Hello everyone, in this video we are going to focus our time on the shades of color in visible light. So we're going to focus on visible light now. Let's go ahead and begin. Okay, so color can be either broken up into several different wavelengths, or it can be combined as white light. White light is not an individual shade of color. Okay, white light is the combination of all of the 7 major colors found in a rainbow. And we'll talk about which colors are found in a rainbow in just a minute. But just know, white light is not a single color. Okay, we can demonstrate this by splitting the white light with a prism. We have sunlight hits a prism, which is angled glass, usually in the shape of a triangle or a pyramid, and then that light bends. And you saw in yesterday's video in class where the different wavelengths hit the angle at different speeds based off of the size of the wavelength, and then that bends them, and as that light bends, it creates or separates a little bit of distance in between each shade of light. Okay, and that's how diffraction works, just the scattering of the light. This is how rainbows are formed, because sunlight is split up by all the different raindrops coming down from the clouds. So the colors of a rainbow. Now you guys had all asked for a couple of mnemonic devices, if possible, on how to memorize this stuff. Not only for the colors in the rainbow, but also the electromagnetic scale. So let me go through a couple of them real quick. Roy G. Biv. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That is your mnemonic device for the colors of the rainbow. Raging Martians invaded Roy G. Biv using X-ray guns. Okay, this I found online, so don't judge it. It's just what I found. Raging Martians invaded Roy G. Biv using X-ray guns. Radio waves, microwaves, infrared rays, visible light, ultraviolet rays, X-rays, and gamma rays. All right, so those are your mnemonic devices for memorizing these orders. Yes, you do need to know both of these in order for your test. This is a picture of all the different wavelengths or the colors of light associated with their particular wavelengths. The longest wavelength is dark red at 700 nanometers. The shortest is 400 nanometers with violet. A shorter wavelength means higher energy. So wavelength gets smaller, energy gets bigger, and it just so happens that frequency also gets bigger. Energy and frequency have a direct relationship. Both of these have an indirect relationship with wavelength. Okay? So just know that the shorter the wavelength, the higher the energy. Let's look at what happens when we split up the different colors of light. Now, the properties of light differ from the properties of pigments. Then pigments are the things you use in art class. All right, if I take red and blue and green paint and I mix them up together, I'm probably going to get something close to black. That is not the case with light. If I mix all 3 of these primary colors together, I get white, not black. And yes, the primary colors in light are red, green, and blue. And that is why your computers and most of your television sets and that dress that I proved was blue and black was able to prove it based off of the RGB scale. RGB, red, green, blue, primary colors. Okay? When I add blue and red together, I get a shade of purple called magenta. When I do blue and green together, I don't get yellow. I get cyan, which is a light color of blue. When I mix red and green together in light, now I get yellow. Okay? So remember, pigment, the effects that pigment play on color is different than the way light works. So how do we see in color? All right, so here is a binder with homework on it, and it's red. And we're hitting it with all visible colors of light. So it's white light, basically from the sun. So how is it that we see red? And we see red because all of the shades of light get absorbed by the binder cover except for the red wavelength. It actually is designed to reflect the red wavelength back out to us. And that is why we see red. Let's look at another example. In our purple pants here, if we hit it with normal everyday white light, so all 7 shades, we're either going to get violet coming off and being reflected, or there's one other option that there could be, and that is a combination of red and blue. Okay, so if you have a shade of color that could be combined by 2 different wavelengths of light, those can be reflected off because when you combine them together, they make that color. Okay, when we have a white hat and we hit it with white light, to maintain that white color, all of the wavelengths of light have to get reflected. So 7 wavelengths of light hit it, 7 wavelengths of light reflect. So how does black work? It actually is the exact opposite of white. If this was a black hat, okay, if this was a black hat and we hit it with white light, all 7 wavelengths would get absorbed and nothing would be reflected, and that would show black. All right, let me show you a couple examples of that. So here is a soccer uniform, red and blue. If I hit it with white light, the shirt reflects red and the shorts reflect blue. So that's why we see red and blue. Now, if I change it up and I change and I make it specific to the color of light that's being hit with it. If I only shine red light onto this outfit, the red gets reflected, so that looks the same. But the red light coming into it by the shorts gets absorbed, because remember, the shorts are blue. And the only shade of color that can reflect is blue. So if I hit it with red light, it actually appears black, because remember, the red light is absorbed. Another example, if we flip it, now we hit it with blue light. The blue light the blue is reflected off of the short, so we see blue. But the red coloration, the red pigment in the shirt absorbs the blue light, so it looks black. Okay, remember, black is the absence of light. So that means that it must be absorbed. Okay, hopefully that makes some sense. If we can add filters in between the white lights, you see this a lot in theater lights, where you'll put filters in front of it to make it a specific wavelength only allows to go through. Okay, so it blocks out the different colors of light. And in summary, light travels in straight lines until it hits a new medium. Light travels much faster than sound. In fact, it travels at 300 million meters per second, where the speed of sound is 340 meters per second. And this is important. Light travels in straight lines until it hits a new medium, and then it looks like it bounces off, okay, or refracts. We see things because they reflect light into our eyes. So the colors you see in your everyday life is the colors that are reflected off of that particular object. Colors are different wavelengths of light, which means they have different energy. The longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. And shadows are formed when light is blocked by an object, which is pretty self-evident if you think about it. Okay, and that is our video for today. Please answer your questions, and I will see you in class. Your video secret number for those of you playing at home is 99. Enjoy, and I'll see you in class.